What we know about double integrals extends naturally to triple integrals. First, recall the notation for double integrals. If we see a double integral over a region R of f of x, y, dA, then we know that R is a rectangular region, the interval AB by the interval CD. And if we see a double integral over D of x, y, dA, then we know that D is a non-rectangular region. The analogous notation that we use for triple integrals is a triple integral over B of f of x, y, z, dv for B a rectangular box. And then it's a triple integral over E of f of x, y, z, dv for a general bounded region E in R3. The two-dimensional trace of the region B is a region R on a coordinate plane. The two-dimensional trace of E is a region D in a coordinate plane. As for the meaning of a triple integral, if the function f of x, y, z is equal to 1 for all ordered triples x, y, z that are in the region B or E, depending on the integral, then the result is a volume. If not, the meaning depends on context, if any, such as mass if the function f of x, y, z is rho of x, y, z, a density function. That's just one example, though. If the region B is a box given by the interval from a to b on the x-axis by the interval c to d on the y-axis by the interval e to f on the z-axis, then we have that the triple integral over b of f of x, y, z dv is equal to the integral from e to f of the integral from c to d of the integral from a to b of f of x, y, z dx, dy, dz. Now, suppose that E is bounded such that z is between two functions u1 of xy and u2 of xy. Y is bounded between two functions h1 of x and h2 of x, and x is between a and b. Then the triple integral over E is equal to the integral from a to b of the integral from h1 of x to h2 of x of the integral from u1 of xy to u2 of xy of f of x, y, z dz, dy, dx. Here we have the limits of z as functions of x and y, so z can depend on x and y. After z is done, y can still depend on x. And after we've integrated with respect to z and with respect to y, we will no longer see those variables in our expression at all, and x, the one that's left, has to have constant limits of integration. And I'm going to make that explicit by writing it here. The outermost integral must have constant limits. In both cases, whether we're talking about the triple integral over b or the triple integral over e, the order of integration matters only in relation to the limits of integration. The integrals are computed pretty much in the way you would expect. We are going to evaluate the iterated integral from 0 to 1 of the integral from 0 to 1 of the integral from 0 to the square root of 1 minus z squared. Our integrand is z divided by y plus 1. The order of integration is dx, dy, dz. As before, we compute the innermost integral first, right? We do this in iterations. That's why it's called an iterated integral. Wow, that little bounding box didn't work out, did it? That's better. So first we're told to integrate with respect to x, and we have limits of x of 0 and 1 minus z squared. With that in mind, what I'd like for you to do is go ahead and compute this entire iterated integral and come back when you're done. Integrating with respect to x gives us the integral of from 0 to 1 of the integral from 0 to 1 of xz over y plus 1, x going from 0 to the square root of 1 minus z squared. We still have dy dz. And evaluating at the limits for x gives us in the numerator z times the square root of 1 minus z squared. And the denominator is still y plus 1. At this point, I note that we have a function that can be factored into a function of z. So from 0 to 1, we have z times the square root of 1 minus z squared dz times a function of y. So then we have that integral is multiplied by the integral from 0 to 1 of 1 over y plus 1 dy. Not a necessary step, but it's one I felt like taking. Looking at the integral from 0 to 1 of z times the square root of 1 minus z squared dz, I notice that u is 1 minus z squared, and so I need to multiply and divide by -2. And after doing that, we can integrate 1 minus z squared using the power rule. So we have -1/2 times 2/3 times the quantity of 1 minus z squared to the 3/2 power. That'll be evaluated from 0 to 1. And then the integral of 1 over y plus 1 dy evaluates to the natural log of y plus 1. Both of those are going from 0 to 1. Plugging in 1 in place of z is going to give me a 0 term. With that minus, it gets offset. So 0 in place of z gives me 1/3. 1 in place of y for the natural log of y plus 1 gives me natural log of 2. And 0 in place of y gives me the natural log of 1, which is 0. So our answer is 1/3 times the natural log of 2.